Hello, Stefan. You're online now.
Hello.
I don't see your screen yet, so let's work on that in a little bit. How are you?
I am super excited to be back. It's amazing. Woo! Thanks for having me. It's a bit nervous like last time, but I guess I hope this goes away through when I'm in the flow.
It will go away. You got this. For those people just tuning in or those who are not watching the agenda, I think, Stefan, your talk is about source generators and implementing an incremental one. Is that right?
That's right.
All right. I'm actually looking forward to this one because there's so much buzz and activity around source generators, people using third-party ones, people building their own. So really curious to see that last part there. Are you good to go?
I'm almost. Give me.
All right. Yeah. We'll give you a couple of more seconds.
Thank you. Just to have everything.
Maybe just to get some buzz going and gauge some interest from the audience here on YouTube and on Twitch. Is anyone building their own source generators right now? Curious to learn about that because I think a lot of people are using them under the hood without even knowing that they might be using it. For example, for Razor in the latest .NET versions or with JSON source generators. But is anyone building their own right now?
Yeah, it'd be interesting to know what use cases people are targeting with that. Yeah. And again, as well, which just to remind everybody, if they have any questions, please fire away in the chats there, and we will follow up with Stefan at the end of the session.
Exactly. Someone is already mentioning that they have a big typewriter library. It's maybe not the same, maybe it is the same. And there's also a question about what source generators are. So I think that's a perfect question to get into your talk.
And I believe I'm ready. Yes.
Yes. Okay. Let's bring up your screen. Let's move us off screen, and then you're good to go.
Great.
All right, good luck.
Thank you very much, Martin. Thank you very much, Matt. Hello, world. It's great to be here at the JetBrains.NET Days 2022. And this session is a bit of a follow-up to last year. It was last year's first session, if I recall correctly, by Andrew, called Source Generators in Action. And he showed the new thing that you can implement, the iSource Generator interface, in order to build this Roslyn component that generates new source code at compile time, unlike other source generation techniques such as reflection emit, which work at runtime. And I'll be basically showing a bit of a diff, so what has changed in the last 1.5 years approximately, quite a bit. And we have a look at, and we will also do a lot of live coding, similar to Andre last time built an iNotify property changed source generator, and we'll be building something with around equality. So let's get started. Title is Never Send a Human to Do a Machine's Job, to quote a famous villain from one of my favorite movies. A little bit about myself. I am Stefan Pölz. I am doing .NET for roughly 10 years. Have started with Roslyn around when the pandemic hit, and doing source generators since they have been released in .NET in the .NET 5 SDK. Currently, I am a senior software developer at Trayport in the office here in Vienna. Trayport is the primary network and platform for the European wholesale energy market, which means there is a good chance that the devices I'm running here to give this presentation are powered by energy which was traded through our platform. However, this talk is entirely my own, and I am also, since recently, a community contributor, a JetBrains community contributor, and a co-organizer of the .NET Austria meetup here in Vienna. I have a couple of socials here if you would like to connect afterwards. I'll link them. I'll supply you with a link at the end. So to a little bit set the stage, what is Roslyn? It's the .NET compiler platform, which includes the compilers for both the C# and the Visual Basic language. We'll be focusing entirely on C# today. And as a consumer of the Roslyn packages, there is a set of NuGet packages that you can consume. You can build plugins, components that your or other people's projects can consume, and then you can supply them via NuGet. So you can build, for example, analyzers. Now, analyzers give you little warnings or errors, the squigglies in your IDE, and they could then be fixed via a code fix provider, which is in Writer the Alt-Enter, or in Visual Studio the Control Dot experience. What Andre showed last time is the I source generator, which you can build in order to generate new sources at compile time. So this was added in .NET 5, and .NET 6 added the I incremental generator because there was a bit of a flaw in the programming model of the source generator, and we will see just at the end of this session what the big benefit of the incremental version is compared to the regular version. Also, since last time, now the BCL team of .NET is also using source generators more and more. So .NET 6 got shipped with 3 source generators actually. A source generator for JSON, a source generator for logging, and a source generator for Blazor. So the Razor files that you write are now actually generating C# code through source generators. And .NET 7 will have 2 additional source generators, one around regular expressions and one about interop, so to replace the DLL import and make that faster. Now, the big advantage of using these source generators over existing versions is that most of the times the source generator can produce very special case code that avoids reflection and then therefore is at runtime significantly faster. In order to utilize source generators, we need a couple of language features. One of the most important language features is partial. So C#2 added partial types, C#3 added partial methods, and in C#9, the rules around partial methods have been relieved a little bit. So previously, with C#3, a partial method must be void, and it is implicitly private. With C#9, partial methods can also return values or have out parameters as well. However, then somebody or something must supply the implementation of this partial method. So it may be a human writing the implementation of the partial method, or it may be a source generator writing this partial method. Today we'll be using a partial type. So the user will be supplying a partial type, and then our generator supplies the rest to that. And C#11, which comes out in about a month, will also include file scoped types, which is a type which is only visible within that file in order to avoid name collisions with already existing types. This doesn't have necessarily only need to be used by generators, but the prime intention of this is to be used by generators. Perhaps a little bit of a refresher since last year's, or it's 1.5 years, I believe, JetBrains.net days. What are the laws of source generation? There are a couple of rules we have to keep in mind. Now, the input to a source generator is basically a set of syntax trees. How this looks like, we'll have a look at in 3 minutes, which include the source code that the user has written. Also, the rest of the compilation, for example, the user's project may include a project reference or a package reference, and these you can all get through the compilation. And via the semantic model, you can ask questions about the syntax of the code, where the syntax tree, basically something is system.string. Now, from a syntactic point of view, we don't know if system.string is the system.string from the BCL, or maybe a system.string that the user may have written because you can. And with the semantic model, you can then actually understand what is the meaning of this string, what members does it have, is it derived, is it implementing something, and so on. Now, source generators are only additive. You cannot change or remove existing code. You can only add new code. And this is where the partial hook comes in handy, where you basically define, the source generator declares the same partial method and extends it with additional functionality. And the output of a source generator is either 0 or any amount of source files, not necessarily files, but source documents. And the result is a string. And this string gets then back into the compilation and is then combined together with the user code. So user code plus generated code is the final compilation. Since generators are technically analyzers, they can also produce diagnostics, such as warnings and errors, perhaps to give the consumer of the generator a little hint about what to do in order to make the source generation possible. And the source generator could also not only consume the C# files as the syntax trees, but also additional files, such as JSON files, for example. One very important thing is source generators are unordered. So one source generator cannot depend on a different source generator. They all get the very same input. With one version of Roslyn, there was a bit of an addition added, so you can circumvent this rule to some degree. We will see this in the example. And the two prevalent use cases for source generators is to avoid tedious implementation. So if you know ahead of time what you are going to implement, such as equality, which will be the example we'll have a look at soon, the source generator can do this automatically, and you don't have to do it by hand and potentially avoid making mistakes. And also, you can avoid reflection. We will also have in the look of an example where reflection is used behind the scene, and therefore reflection allocates and is not the fastest because that's runtime evaluated. And we are going to replace that via a special case implementation, which takes the logic to the compiler and then at runtime is fast and doesn't allocate on the heap. Okay, so before we jump into the action, what we saw last time was version 3.8 of Roslyn generators, the I source generator. There was version 3.9, which adds post-initialization. We will see this in the example. And in Roslyn 4.0, incremental generators have been added. And this is the generator, the programming model that we will build right now. So let's jump into the solution. What I have here is a type. I called it the equality comparer generator. So this generator will be creating equality comparers, and it's deriving from, well, no, it's not deriving from, it's implementing the I incremental generator. We also add the generator attribute on this generator type and give a hint that this is a C# generator, because you could also write a generator which emits Visual Basic code. But now let's have a look at the problem. So I have a set of tests here that I will run. And we will be seeing that something is failing. We get the exception, the given key was not present in the dictionary. The example that we have is, we have a dictionary, we have a my class. Now I assume, or we assume here, that this my class is outside of our control. This is not a class that we have written. It may be coming from a third-party library, so we have no influence on this type. We cannot extend it. We cannot implement equality on it. And as we see in the type, it doesn't implement equality. So since this is a class, reference equality is used and not value equality. And therefore, if we add an instance of the my class with the integer 1 and the string 1 into this dictionary and then try to get that value again, not by reference, but with the same value, we don't find it because it's a different reference. And we would like to use, what we could now do is, because we cannot change the my class, we cannot implement equality on that, we could build our own equality comparer. And I already ahead of time know exactly what I would build. I would build an equality comparer, which is generic of this class, and then basically compares all the members. So it compares the number and also the text. So I know already ahead of time what I would be building. So we can put this into a source generator and have the source generator automatically generating this for us. And another example that we hear, what if we do this with a struct? Now with a struct, this test is passing. With a struct, this works because every struct is implicitly deriving from value type. If we have a look, my struct, the base type is actually value type. And value type has some implementations for us. So it implements equality and also get hashcode. However, there are caveats to this implementation. Now let's run a set of benchmarks. In release mode and with the Net 6 framework. And while we do that, we have a look at the value type. So we will jump to, I'll go to the site sites of .NET, which links a lot of interesting pages and sites. For example, there is the Roslyn, the source roslyn.io, which is a source browser for Roslyn. And we also have source.net, a source browser for the BCL and the .NET runtime. So let's have a look at the system.valueType. And we see that equality is implemented. There is this one is a rather fast check. However, this is only applied if we can compare bits. Now, what does this mean? Let's go to the repository. Let's go find this can compare bits. There it is. And there is a comment. So can compare bits only works if the struct, if this value type does not contain any pointers. Our struct consists of an integer and a string. The string is a reference type, so we do have a pointer there. Or if it's tightly packed, so this amounts to the layout, the memory layout of a struct, if there is padding or not. Or if we have a floating point number, then we cannot compare the bits. And if we cannot compare the bits, then we will actually fall back to what we actually see here, a reflection-based implementation. We get the fields and do equality reflection-based. Now this will allocate. This allocates here and is also slower than a more naive implementation. And the get hash code, if we have a look at the get hash code, it actually says this is the current version of the BCL. This may change in the future, but since the algorithm of determining a hash code dynamically is rather complicated, so we are only comparing the first non-static field. Now this means in our example, our myStruct, which consists of an integer number and a string text. So we have a reference in here. We cannot compare the bits, so we need to use reflection for equality, but also the get hash code causes issue because only the number is observed. Now, if the struct differs in the text, then we actually have a hash code collision. And if we have a look at some benchmarks, which unfortunately have failed, well, it's not that important, but what we would have seen in this benchmark, where we create both a dictionary with the key of the my class reference type and one with the key of the my struct, we would see that this method would actually allocate, because we have hash code collisions, because there is no difference between so we have hash code collisions, but also we use equality because of the hash code collisions, and this allocates. So this is slow. So we are going to fix two issues with this generator by auto-implementing equality comparers. Now, what I did ahead of time is create a set of unit tests. I strongly advise, if you build a source generator, to have unit tests around it, because this is also, each and every unit test is also a great entry point for debugging, and this is really, really helpful. So what we see, we are consuming the Microsoft Code Analysis C# source generators.testing.xunit. There is also an MS test and an NUnit variant of these packages, and we can use these to unit test our source generators. There's also other versions, other approaches such as snapshot testing, but here we are going to focus on this more low-level package. And so we first have here our unit test when we just have a class. So the input to a source generator is basically just text. So we will write here some C# code. And if we pass in just an empty string, then nothing is generated. We basically assert here that we only emit a specific attribute. So this is here an attribute. I called it the equality comparer attribute, which gets a type that we will use in order to determine for which type the equality comparer should be generic on. And if we had C#11 already, we could actually make generic types like so. We could have a generic attribute of t, but since we are still on C#10 here, I have to fall back to, or not fall back, but still use the bit of the soon old-fashioned type of version of an attribute. And this will be not only a marker attribute, but it will also hold the information about which type we should generate equality for. And so if we have nothing where we place this attribute on, nothing additional will be generated. However, if we do, so this is how the generator then could look like. We define our own partial class, and we slap this attribute on top, where we say, please implement equality for the my class type, where we declare the my class here. It's the same that we saw from the example and consists of a number and a text. Could be any amount of properties. Our source generator will inspect all the properties. Should also inspect fields, but for now we keep it simple and only properties. And then the expected text should be something like this. We always add auto-generated on top of generated code. This is a good practice so that tooling understands, okay, this is generated code. Emitting diagnostics such as warnings and errors for that is maybe not, well, errors is something else, but warnings is not really super helpful, because the user who is consuming the generator doesn't really have direct influence about what the generator is producing and can't necessarily fix the warnings. And then we're gonna extend this comparer that we slapped the attribute on. And we're gonna implement the I equality comparer. What I'm doing here, I'm not writing any using declarations. I'm referring to the I equality comparer name in the full qualified name, including the global alias, in order to avoid potential name clashes, because technically the user's project could implement their own system.collections.generic.iEquality comparer interface, and by referring to the global namespace alias, we could avoid potential name clashes. Then we're going to have a private constructor because we will apply the singleton pattern, because an equality comparer doesn't really have observable state. So the singleton pattern is a good fit here. And then we will emit those two methods, so the equal methods from the interface and the get hashcode method, where we do, since this is a class, we do some null checking and then compare each member by using the default equality comparer. So we use the integer comparison for both the number of the left and the right instance, and combine this with the string, which is the text property of that class, also equal check. And here we see another good practice to put the CodeDOM compiler generated code attribute on top of generated methods or generated types, so that, for example, reflection-based tooling can't really read this comment because it's not there. But reflection-based tooling can read attributes because they persist in the metadata of the assembly. So reflection-based tools would understand that also this is a generated method, not directly written by the user, but some tool, and we pass in the name and the version of this tool, perhaps also for debugging purposes. And the other method that we need to implement due to the equality comparer interface is the get hashcode, where we get in the my class, we check for null, and if it is null, we hashcode combine all the members. Then we verify that this has actually been generated. So here is a bit of a hint name. What's this? It's not really necessarily a file that the generator is producing, but we will have a look later on of how this could look like. There is a flag to emit the file to disk to have a physical look at it. Otherwise, it's just in memory or in flight in the compiler steps. And then we have a second type for if we define an equality comparer type of myStruct, so which is a value type. Since a value type can't be null, well, not in the terms of a nullable reference type, we don't need the null checks, and we just, in the equals and the get hashcode implementation, we just combine the members. And now we're going to write the generator to auto implement all of that. So let's jump to in the generator. And if we have a look at the interface, the incremental generator interface, there is only one thing. There is only the initialize method. This is different to iSource generators that we saw in last year's JetBrains.net days, where there is an initialize and also an execute. Here we only have an initialize. And in this initialize, we're going to build up our pipeline. But first, let's have a look at our first failing unit test. So our first test, which only expects the attribute to be generated, doesn't really generate anything because it says we expected 2 sources but have only 1. So there is only the one source that the user supplied, but no generated version. So in that case, we want to emit this attribute. And since we always need this attribute unconditionally, we can use the thing that I mentioned earlier, the initialization, post-initialization, that was added in Roslyn 3.9. So we can say in this context, we can say register post-initialization output, and we will call the method the post-initialization callback, which gets the incremental generator post-initialization context. And we see from this type, this only has a cancellation token and a method to add a source. We have no compilation, we have no information about any syntax trees or anything. So we can just unconditionally emit some source code. And we will do this with our attribute. So we will say context.add source. And now we give that thing a name. We will be using Roslyn.generated.equalityComparer attribute.g.cs. So this is the full qualified name. It includes the namespace and also the name of the attribute that we are adding. And at the end, we always add .g.cs to, again, it's good practice to indicate tooling that this is a generated file. We could also write the full generated.cs. It's the other convention to indicate this is a generated file or a generated source. And then we're going to refer to the attribute. We defined the attribute that we had a look at already. This very attribute, we will now put emit. And if we run this test, it should turn green in just a second, and it did. The test has passed. So we now are emitting unconditionally this attribute that now the user can consume and put on their types in order to give an entry point to the source generator. And so actually, let's have a look at how this could look like in action. If we go to an example project, what we can now do is, let's say, we can say our internal class, my comparer. I call it the my struct comparer. Just an empty class. It should be partial so that the source generator can add a source to it. And we're gonna put the equality comparer attribute. And we will say type of my, type of my struct. And we will see if I go to the source of this equality comparer attribute, we will see writer, and it's very, very similar in Visual Studio, shows this with a yellow background that this is a generated file. If I would try editing it, writer gives me a hint, hey, this is a generated file. It doesn't really make sense to change it. And this is what the generator is creating. We have the auto-generated comment. We enable nullability. We put the generated code attribute and emit this attribute that now can be used within this project. But nothing is really generated yet. So the end goal should be that I can say, because a dictionary, if we have a look at the implementation of a dictionary, one overload takes an equality comparer, and we want to utilize that extension point. But the MyStruct comparer currently has no members yet. We still need to emit them. So let's go back to the generator. The next failing test is now that we need the actual thing generated. And now we gonna start the pipeline, which is the core programming model of incremental generators. If we have a look in the, this is the wrong method, sorry, in the initialize method, the one that is from the interface, we can have a look at this initialization context. And this initialization context has a lot of properties. Most of them are either value or values provider. And this is very comparable to, it's not exactly, but it's comparable to link, like an I enumerable. So this is a deferred evaluated pipeline that then the actual source generator driver is executing, where the driver could be our writer IDE or Visual Studio IDE or the .NET CLI, .NET build, for example. And we have a value provider with singular, so we can get a hold of the compilation. We can also get a hold of the parse options. The parse options, for example, include information such as the language version that this project was compiled with, in our case, C#10. We can also get additional texts, because there could be no additional texts or many additional texts, for example, a JSON file or an XML file. This is a so-called values provider, plural. There could be more or none at all. We also have analyzer config options, and metadata reference. This, however, is a bug in the version that I'm using here. I'm mostly using version 4.0. This was fixed in version 4.2, where this is actually a values provider because there could be more than one metadata reference. And we have a syntax value provider. With the syntax value provider, we can have a look at all the syntax nodes. Now, why would we need that? Let's again go back to our example and let's have a look at this code. If we put this into sharplab.io, which can not only decompile our source code, but also give us a way to inspect the tree, we can have a look. If we go to the syntax tree of it, we see how this C# code looks from a syntax tree point of view. So everything is in the compilation unit. Now this compilation unit has one class declaration. This class declaration has an attribute list. And those are all nodes. All the blue ones are nodes in this trees, in this syntax tree. And the attribute list has an attribute. It could have multiple attributes because we could have more than just one attribute on top of a member or on a type. And one of these attributes, it has an identifier and an argument list. And in this argument list, we eventually come to the type of expression. So we need to drill down. What we need to do is now find all the classes, all the partial classes in the compilation that actually do have this attribute applied to, and then inspect this type of expression in order to get to this identifier name. If I highlight it here, we see this is the mystruct identifier name. And this is how we can extract the information out of this attribute in order to generate the right thing. So we are going to build use the syntax provider. So we will say context.syntaxprovider.create syntax provider. Now this takes two callbacks. One callback receives each and every syntax node in this tree and a cancellation token and returns Boolean. So this is a quick filter to see, is this interesting for us, this node? And as a second part, we have a transform. Now this transform is semantic because this generator context also gives us the semantic model to give meaning to our code. And utilizing both, we can now, I have the two methods prepared already. We can have a look at the syntax, the syntactic predicate and the semantic transform. Store this into our pipeline. Okay. And now it's to implement the syntactic predicate. So we get in each and every node of this compilation. So if we jump back to SharpLab, we get in all the nodes. So we get in the class declaration, the attribute, and if there is more, there could be other classes. So we get in all the nodes, and we need to filter which nodes are potentially interesting to us. And with that, I'm gonna bring in this code. So we will inspect each and every node, and if this node is of type class declaration, this is exactly what we saw in SharpLab. If we jump back, we see it's this class declaration that we search for. And if it is, we also should filter if this class declaration has at least one attribute on it. It may not be the attribute that we actually care about, but it's a candidate, because we only can have a look at the syntax here. We don't know the semantics here. So just have a look at this code. We don't really know if this equality comparer attribute is actually the ones that we observe, or it's some other equality comparer attribute that the user or some other third-party library has defined. So from a syntactic point of view, we only know we need at least one attribute in the list. And then this candidate, we also check if the modifiers, again, jumping back to the code, the modifiers are these. So we have a partial modifier and a class modifier. And we see, no, class is not a modifier, but we have a partial modifier, but we could also have a static modifier. But because we want to implement an interface, static wouldn't make sense. Static type can't implement interfaces. So we will have a look at if the modifiers, if we have the partial keyword, and we do not have the static keyword in this modifiers collection. And now this thing is a candidate. It could be one of the methods, one of the types that we want to generate source code for. And now after this syntactic check, every syntactic check which returns true will get fed into the semantic transform. And for that, we will bring in a little bit more code where we now know. So we have here the generator syntax context, and this has two things: the node that we previously filtered, so we know this is a candidate, and the semantic model. So we can ask semantic questions about this. We can get type information about this node. And so we know, okay, this node is a class declaration. We filtered it previously. We will cast it to our candidate. And we then get, via the semantic model of this class declaration, we get the type information. And we also check if this is a named type. It should be like, for example, an anonymous type is not a named type. But every class declaration that we usually write in code, that is a named type. And now we check, via the semantic model, we can also get a hold of the compilation. And we can get types by metadata. So we grab both the equality comparer interface and also this Roslyn generated equality comparer attribute. Now this is the attribute that we have emitted in the post initialization. Now what I said previously, source generators cannot depend on each other. However, in the post initialization step, if we emit source code in the post initialization step, source generators can actually see and inspect that. If it was in the execution phase of another generator, then it wouldn't be available just yet. And then we check if of this type, if we jump back to SharpLab, of this very type, we see if it already has this equality comparer attribute. Let me structure this a little. If it has already this equality comparer interface implemented, because if it's already implemented, then the source doesn't make sense to implement it yet again. And if it's not implemented, now it's time to get a hold of this information, because we need to drill down into this very attribute and get this my struct information out of that. And for that, I built a try get attribute info method where we pass in our candidate, the attribute that we are scoping for, and the semantic model to ask additional questions about that. And here we're going to bring in more code where, since we need here a double for loop, because attributes in C# we could have attributes like this, and each of them is one attribute list. But within one attribute list, we could also have something like this, comma separated attributes. So this is multiple attributes in one attribute list. This is why we need this double loop. So we first loop through all the attribute lists, and then we grab all the attributes in this attribute list. And we get, again, via the semantic model, the type information out of that to understand what is that. And we want to get a hold of the argument list. So if we again drill down to the original source code, this here is the argument list. We see that here, the attribute argument, because we want to get a hold of this type of expression. So we will have a look if the count is exactly 1, because then it is what we want. We get a hold of this argument. We check if it is indeed the type of expression that we just saw. And with this type of expression, we can once again ask the semantic model about the type information of this. And we get a hold of the symbol. And now we have the type. This now actually returns us the type information about this my struct that we have here. This could also be my class, or it could be string potentially, any type that we want to implement equality for. And if we found that, we return true, otherwise we return false. And at the end, we return a combination of both the static type, not the static type, but this the type that we put the attribute on, that we want to, the partial type that we want to extend, and also the symbol of the type of expression to know which type to generate equality for. And with that, we're gonna implement a bit more in the pipeline. Since I have now, we basically now did the most important part. We have all the types that we need. Now it's time to basically bring the pieces together and start generating the code. So I will extend the pipeline now. I have an additional filter. So this is each and every method here is another step in this pipeline. First, we filter all the types which do not have any value, because we return null in this semantic transform here if we didn't find anything interesting. And then we're going to transform this type. I will implement this code rather quickly. We're not scoping into much detail because it's not really Roslyn specific, but what we basically do is get all the information that we need. We get the namespace. It's important to understand if a type is in the global namespace or is in a named namespace. This could cause potential issues if we do not do this check. We get the name of this partial type. We want to understand, is it a reference type or is it a value type, in order to generate the right thing with the null checks and so on. If it is a reference type, we actually want to add a question mark at the end, because we have nullable enabled. iEquality comparer is annotated such as that it could take null as an argument to the methods. And then we go through all the members that are properties of this type. So in our case, the my struct, we will get a hold of these attributes, and we get the name and also the type, because this is the information that we need in order to generate the code. And just filling in a couple of more gaps in here. And now we have extracted all of this information into this partial class context. This is just a record struct. We have the namespace, the name, is it a reference type, and all the information that we need to generate the code. And now we can actually get generating. So this is the last piece of code that I will bring in. This is now in the execute phase of the compilation. So if we jump up here, we actually still need to implement it. So we can say via the context, we can now finally call the add the register source output. So this will actually be used in order to generate the source code. We will pass in our provider that we have built. and also tell him to run this execute method. And here we have now a bunch of code. I'll briefly skim over it. So we have here the null checks in place if it is a reference type. Some more null checks if it is a reference type. And then we generate the source. Since the result is just a string, we assemble here a string. You could also use a string builder or other means of how to generate this source code. So we have the auto-generated attribute, nullable enable. Now if, this is basically saying if the type is in the global namespace, we shouldn't emit namespace, because if it was, the code would actually look like something like this, namespace global, and this wouldn't compile. So if it's in the global namespace, we do not declare a namespace, but if it is in a named namespace, we emit that namespace. Then we generate this partial class. It implements the iEquality comparer interface. Here we have the private constructor that we saw. Here is the singleton instance member, and we generate both the equals and the get hash code by going through all the properties and emitting these equality comparers. And then at the end, we give this thing a name via the hint name and put the source into production. And if we build that and jump back to our example here. Now, if I go to the dictionary, previously I entered the type and then say dot. Now we actually have the instance available. This is generated by the generator. We still don't see it here, but if we have a look, we can go in wider to the source explorer, go to the dependencies tab, have a look at the source generators. So we can go down this trail, dependencies, target framework, source generators. We see here our source generator that we have built and all the code that it emits. This is not necessarily files, but the hint name that we gave, we actually see here in the tooling. This is why it's called a hint name. So tooling can pick it up and give this a name. And here we have this one file is the attribute that we generate via post initialization. And here is our actual implementation of the comparer. So here's our partial class struct comparer. It implements equality of the myStruct type that we have declared, that we have extracted from the type of expression of the attribute. And we have all the implementation ready, and we compare the numbers and also the texts. And for hash code, we hash combine it. And we can also do the same for the class. So we can have my class here, and we are going to call this the my class comparer, and put the instance here. Now I'm afraid wider needs a brief restart. And all of these should turn colorful in just a second. Here we are. And now we can run this benchmarks again if I fixed the unused field. Yes. And while this runs, let's also have a look at our tests. So the other example that I showed was this test where we couldn't, this should be here, there they are, where we have an issue of finding this class again because we use reference equality. So again, let me create an internal class, my comparer. I put the equality comparer attribute that was emitted in the post initialization phase of the generator, type of my class. That's it. The rest, oh no, we still have to make it partial so that the generator can extend it. And now we can, in this example here, add my comparer.instance again, generated by the generator. And if we run this test, which previously failed because the given key was not present in the dictionary, now we are using this generated equality comparer, and this test will turn green in just a second. There it is. Now it's green because it's now referring to this equality comparer that no longer uses reference equality, but value equality semantics. And also the benchmarks should be done. And the benchmarks previously failed. I'm sorry for that. But what we would have seen is that we would have allocated a couple of bytes here, because for the value type, reflection under the hood would have been used in order to determine equality. And since this is no longer the case, we now have 0 allocation. And this is basically how you could build your own generator to avoid slower runtime-based implementations, such as reflection, while not really having to do anything. So for the consumer, it's super, super convenient to just, where's my example? There it is. To just define a couple of types, put an attribute on it, say the target type, and that's it. And the user is free to use any type name that they want, put it in any namespace that they want, and use it wherever they want. Now, since this is the testing that we have, is really, really important also for debugging. So if we have a look at our generator, let's perhaps get, where is an interesting part of it? Let's jump into here. So we can actually debug the unit test. To serve as an entry point for debugging, yeah. And we will hit this breakpoint in just a second. There it is. And oh, I closed it. And since this is basically, the Roslyn is super extendable and it's with this package very nicely testable, we can have a look at all the nodes. So we will have call stacks, and we can inspect, we can evaluate all the values and have a look at, okay, what's available, what information can I extract. And since this is if we have this unit test, also another nice side effect is that we can use mutation testing and code coverage. So let me run some mutation tests. I'm using striker.net for that, which is a mutation testing framework. And while striker.net is running, just making sure that everything is all right. It found test run successful. Now it should determine some mutants. Yeah, that looks good. While this is running, we can also use Rider to inspect code coverage. So let's cover all of our tests. Did I click it? Cover all tests. Doing something wrong. Cover all tests. Still building. Not sure what's going on, but yeah, we would have seen that we got pretty good code coverage and we get the green gutters at the end. And mutation testing is almost complete. We will get a nice report of our test efficiency, where we can actually see, if we drill down a little bit, where do we have something interesting in place? Some mutant that I hit. Yeah. So here, the mutation testing changed this end into an OR, but we do not have any failing test So my test suite is not super efficient yet. I need more cases around implementing interfaces to make it more reliable. And for the last part of the session, we actually wanted to reap the benefit of the incremental generator, because we have one little issue. Jumping back to our example, if we open both generated files, because we both generated types, we generate 2 of them. If we open them side by side, and in the generator would add a where's my generator? There it is. Oops, sorry. So, in the output, in the emitted code, if we would add the current date of time, datetime.now, oops, and build that. Where are my generated files? Here they are. All right. If you have a look at these timestamps here, and if I change, so now I have everything set up. If I change any code, let's say I add a enter just here, the timestamp will change. So we have 1426, and if we do that, it will soon jump to, oops, I think I gave the conclusion away, haven't I? Yes, because I already implemented the last bit, sorry. Let me comment this out and run the example again. And if we hit return now, so the current timestamp is 12:15:30, and it will soon jump to 12:15:36, and I will hit enter just again, and it jumps to 22. And although I haven't changed anything interesting in the types that we observe, we still generate everything anew. And this is now where the power of incremental source generation kicks in. So as one step of the pipeline, I here define a comparer. And this is now used to compare the results of the individual steps. And if, so the pipeline that we built, if in the second run of the generator, if one step of the pipeline creates the same result as in the first run, then subsequent steps of this pipeline, such as emitting the source code, can be skipped and just reused, because same input, same output. Source generators should be deterministic. And now with this comparer in place, if I rebuild, we have now fixed this flaw. And this is the real power of the incremental source generator pipeline that we just built. Now the timestamp is 12:16:44, and I remove a couple of enters, and I wait 3 seconds, and this will not change. It will stay at 12:16:45. The code has not been generated again. However, if I, for example, in this class now change text, I rename text into name. Now something actually has changed, and it should be generated again, but only a part of it. So we will see that the myClass comparer now has a newer timestamp, but the myStruct comparer that hasn't changed was still reused. And this is the power of the incremental generator pipeline. So in IDE scenarios, because actually Microsoft hit this problem in the BCL, they have had in Visual Studio and also in wider a bad developer experience, because everything was generated all over again. And with incremental generators, we can circumvent this potential flaw in huge solutions. In a smaller solution, you will not notice any issues. And with that, coming back to the slides. So here are a couple of best practices. This is all online if you want to have a look at it again. We had a look at to add auto-generated, to use the global alias, use the generated code attribute, the hint name. Be mindful about the language version. So I'm emitting here C#10 code because I'm using file scope namespaces. So if a project that is compiled against C#9 would consume this generator, compilation would fail because the language versions do not match. So we need to think about the target audience. Always do benchmark, always do testing, and keep in mind that generators should be deterministic. I have a link to a template that I actually used in order to kickstart a source generator project. And with that, I list here the link to the presentation and also to the source code. And if you follow this website, you could click some of my socials if you would like to follow up later on. But perhaps you have a question right away.
All right, let's bring us in. Thank you, Stefan. Fantastic talk as always. I love seeing you present, and actually I have a nice compliment there for you. Great presentation style with all of the arrows and marking on screen. And I do want to start with the most important question first. What's the tool you use for marking on screen?
That's oops, sorry, I hit the wrong key. Why does it? There it is. So it's a tool called Zoomit. It's part of the sysinternals suite, and with that you can type and zoom and also change colors. And yeah, I cannot do anything without this tool anymore, and this is why I'm always bound to Windows now.
You're a genius at that, it has to be said.
Yeah, exactly.
Thank you.
Also, some nice comments in the chats of people building their own source generators and using source generators. So someone was using source generators to simplify durable orchestrations in Azure to remove some boilerplate codes. Someone else was using or building a source generator to generate record types for classes in a project with an older C# version, which apparently was a bit flaky on some developer machines. Others are using it to build test suites, so really lots of source generator usage. So thank you for inspiring many more people on getting that knowledge spread a little bit. Maybe one question that is very interesting as well. What do you see as a big difference between source generators and text templates like T4 and things like that?
Well, for example, T4 templates, this is Visual Studio only, I believe. So this is heavily depending on the tool, such as the IDE that you're using. But source generators and incremental generators, they are part of the .NET SDK. So I'm using Rider here. You could also use Visual Studio. You could also use Visual Studio Code or just edit it in Notepad or anything because it's part of the SDK. Well, of course, Visual Studio and Rider both have additional toolings, such as viewing the files in the tree, which makes it easier. But it's in the core, it's tool independent. As long as you have .NET installed and reference the Roslyn package, you can make use of source generators. And also, you get as the big advantages you get as an input the syntax tree of the user, so you can react to what the user types as the user types, and then you see on the screen that the generated code changes as well. So this is a very nice experience when exploring source generators and starting to work with them.
Cool. So it was a very interesting description of incremental source generators. And obviously, we've got now a new API for doing incremental source generators as opposed to just a source generator. Is there a big difference between the two? I mean, obviously, it's a bit more of an involved API, but which one would you prefer to do?
So I would... If you don't know the target audience, so if you're publishing this as a NuGet package, and basically the world could be the consumers, then I would definitely go for an incremental generator, because if the consumer has a huge solution and huge projects, then with the non-incremental version, where basically on every key press, everything is generated again, this would deteriorate the developer experience. So for these, definitely use incremental generators because of this, of the pipeline effect that I showed at the end, where the incremental generator can short circuit for subsequent generation phases to not emit the same thing again and then be faster about it. However, I guess starting with the regular, if you want to get your hands dirty with generators, then perhaps start with the regular .NET 5 iSource generator, because the programming model is a little bit easier. You don't have to think about the value providers and this pipeline to build up. So this is a great way to get familiar with source generators in general and the Roslyn API, with source generators in particular and the Roslyn API in general. But for production ready generators, I would use incrementals.
Yeah, makes sense. Maybe also an interesting question from someone in the audience. Is there any tool for emitting C# sources? So far, most people are string building. There's also syntax trees, but they are a nightmare to format and work with and maintain. So what could be a good middle ground there?
There is, I haven't checked it out myself yet, but there is a templating, a C# string templating library called Scribian or Scriben, where you basically define a template and then later on fill the holes. I haven't used it myself, but this could be an alternative. But what you definitely should keep in mind that the mean how to generate this C# string should be fast in order to not be a bottleneck in the editor experience.
Cool. I may actually add something myself there as well. And I took the liberty of cloning one of your repos that you have. If you're using the newer version of Rider, the latest EAP actually, we are reworking some of the language engine. And actually, if you add a language injection saying that this code is C#, you will get syntax highlighting inside of the C# strings we have. So that's a really nice one to demo, but also a really nice one to work with source generators.
Mm-hmm. Instead of just having a plain block of string literal, you've got something which is a bit more syntax highlighted. That's nice. I like that.
And I guess this will then, since C# 11 also will add raw string literals, where you have if we have a string interpolation, then this will be beautiful. Is this already, or is this in the current preview?
If you use the latest preview, you will be able to use this one. Yes.
I'll use the latest preview today.
Perfect.
Awesome. I think also there's been some work so that Rider should automatically pick up and restart the Roslyn host, so that you don't have to reload the project as well when you change the source generator. So hopefully that will.
It actually works most of the times.
Very good.
It's just sometimes I have to restart it, but usually, of course, now presentation effect. Usually, it actually works without restarting. Just hitting rebuild, and it works. Not always, but most of the times.
Cool. Okay. Last question. Then I think there was a great question there saying, is it possible to generate embedded resources, either text or binary, as a project? Does it? Because you're putting in a string there. So can you put in a string of anything, or does it have to be C#? Not
yet. So currently you can only add sources, either C# or Visual Basic. However, the input could be C# or Visual Basic code or any arbitrary additional text file, but output is source text only so far. This may change in the future though. Okay, that sounds cool. Right, well, thank you very much for your presentation. It was absolutely brilliant, and yes, it's a fascinating topic. And it's also interesting from the examples in the chat that you can do it. You can apply it to a lot of different things. So, thank you very much.